on the next page. I put the formulas, shockingly, I put them on each page for a change. Or at least I tried to. So I plotted the spherical coordinates for some reason and still told you to plot them. I can't stop myself, I don't know why. Honestly, I'd never ask you to plot them because they're a pain. But what we want to do is express it in rectangular form. All right, so expressing it in rectangular form is mere child's play, as long as you have those rules, because I just need x, y, and z. All right, but the key is understanding what these spherical coordinates are telling you. And so just go in shape. All right, so rho, theta, phi. Refer to your formulas. We have 8 sine of phi, so sine of pi over 6, cosine of theta, which is pi over 3. All right. Then we're going to have 8 sine of pi over 6, not cosine, sine of pi over 3. And then the last one is going to be 8 cosine of pi over 6. All right. Unit circle. Always unit circle. Well, fortunately, the sine of pi over 6 and the cosine of pi over 3 are the same thing. They're both equal to what? 1/2. So we're talking about 1/2 times 1/2 times 8.
2.
So 2. All right. The second one, a little different story. Because we got the sine of pi over 3. But sine of pi over 6 is still 1/2, so we have a 4 here. 8 times 1/2 is 4. What's the sine of pi over 3? Square root of 3 over 2. So 4 multiplied by the square root of 3 over 2.
2 times the square root of 3.
2 times the square root of 3. And then we just need 8 multiplied by, what's the cosine of pi over 6? Cosine.
Oh. Square root of 3 over 2.
Square root of 3 over 2. All right, so we're looking at 4 root 3. So in rectangular coordinates, we'd have 2 root 3, and then 4 root 3. All right. So that's by points. In terms of equations, can be a little dicey, but sometimes it's not bad. Like for example, in part A, it's saying that rho is equal to 13, but we know that rho squared is equal to x squared plus y squared plus z squared. So I'll square both sides. Rho squared is equal to 169, in which case we would get x squared plus y squared plus z squared is equal to 169. All right, so that's a sphere with radius equal to 13. All right, that's great news, because what that did was it took a really complicated rectangular equation, or it will take a really complicated rectangular equation and make it a very, very simple spherical equation. All right, just like when you're dealing with polar coordinates, converting a circle equation into polar form takes something complicated, makes it easy. This takes something that's more complicated and makes it easy.
We're dealing with the cylindrical coordinates. Is the theta still theta?
Theta is still theta.
Okay.
Right. That animation I sent, or the applet that I sent out earlier today, that'll help you get a sense of movement within the spherical system. All right. Okay, so then we have theta is equal to 2 pi over 3. All right, so that's a little bit of a different story. because it doesn't really seem like we have much to go on here. All right, but we can like I was saying before, sometimes it's helpful to stop off somewhere.
Well, the tangent of theta is y over x.
Right, it's right there. Yeah, so theta is equal to 2 pi over 3. Just make the slight adjustment by taking the tangent of both sides. All right, so tangent of theta would be equal to tangent of 2 pi over 3. All right, so that's your intermediate step where you're actually just operating on this, and then we could apply this rule saying that tangent of theta is equal to y over x. We just need to know what the tangent of 2 pi over 3 is. No, 3 pi over 2 would be undefined.
Isn't that negative square root of 3 divided by 2? No, I'm sorry, square root of 3 divided by 2 divided by negative 1/2? Or the way around?
That would simplify to it.
Yeah.
So negative square root of 3 is what that would end up being.
Yeah.
And so y equals negative root 3 times x, which is going to be a plane. All right, and then for C, that's probably the juiciest one. We have phi equal to pi over 4. All right, we have a relationship that involves phi, so I can make that substitution, the arc cosine of all that fun stuff, which is the definition of fun. Let me just do it this way. So arc cosine of, like I said, all this good business here. Look at that. Oof. And by the way, this has a basis in that diagram. If you actually, and I'll just refer to it very quickly, but that's fairly typical. All right, so I'm going to take the cosine of both sides, and we're going to get z over all that good stuff again. What is the cosine of pi over 4? Square root of 2 over 2. All right, I got a radical there. I don't want it, so I'm going to square both sides. So z squared over all that jazz is equal to 1/2. Cross multiply. X squared plus y squared plus z squared equals 2z squared. Or you could say x squared plus y squared minus z squared equals 0. Now that, I don't know, maybe not, it's 0 on my screen. That's so weird. That may not be instantly recognizable, although if you make some headway in that tech assignment, it starts becoming more recognizable. We have talked about this before, but what I'm going to do is I'll solve it for z in terms of x and y. So if I move the z squared to the other side, I'm going to get this. That we've definitely worked with. That's a hyperboloid of one sheet.
How does
All right. So we have tackled this. This is that's the case of the cone that's tip to tip. Right? That's what this is, the equation. Now, nasty, yes, in any form. Not nasty. I would imagine that I needed to integrate this. That's not going to be difficult, right? So, but integrating something involving all of this, we've already seen that before, all right? So that is not my scroller, all right? So that's your motivation there, really, more than anything else. The last problem here is really just evaluating the triple integral, but it's already converted into spherical coordinates. So I'm just going to put a star on this one because even though the notation's different, I mean, just imagine they're x, y's, and z's, and you'll be fine. There's nothing to it. What we're going to do on Tuesday is we're going to learn how to convert from x, y, z form into spherical form, and also from cylindrical form into spherical form, so that you can apply integration techniques along these lines, all right? And that'll be the last topic of the course, and then test, we've already talked about it.
Can I see the solution for 2C again?
Say again?
The solution for 2C?
2C, there you go. All right, so if you came in late, check me before you go, otherwise have a wonderful evening.
Quickly, Professor. I mentioned in last class about the Manhattan College. Can I just shoot you an email? Just
Yeah, send me the email because I'm going to completely
All right,
forget.
thanks.
Professor, I don't get what's going on right here. When we
In which step?
when we're taking the bottom of this and making it equal is 2 times z squared. I don't know where that came from.
The bottom and equal.
Of this fraction right there.
Oh, here.
Yeah.
Oh, cross multiply.
Oh, you cross multiply.
Yeah.
Ah, there we go. Okay.
I came in late.
Okay, I get you.
And I appreciate the notification.
Oh yeah, I knew you had it. It was just a question of like I didn't have it, so I didn't want to give you a zero.
I really appreciate that. Thank you.
No problem, bud.
I was late.
Okay, I got you. What's that? I got you already.
Also, I wanted to talk to you about my grades.
Right, yeah. So I haven't put together my spreadsheet yet, which is what I use to formulate the what if scenario. So if you could just give me a day, because I was going to sit down tomorrow and create the spreadsheet for everyone, and then I'll be able to run numbers for you. All right. Anyone else for attendance? I got you.
Okay.
Yeah, I got you too. Yep.
2 weeks, bro. Wait, what's in 2 weeks?
I have a question. So at WCC, I'm part of this thing called the Workplace Culture Coaching Program, and there's this graduation for it, which is during it's next Thursday.
During the most inconvenient time ever.
Yes,
Yeah.
exactly. It's from 5:30 to I think 9 or 8.
Okay.
So I know we have to test that day. I don't know if I can take it a bit sooner or or I don't know
Yeah,
any other way
I
to
mean,
arrange that.
totally.
I don't want to be an inconvenience to you either.
No, it's not a problem. I gotta figure out logistics because I'm only really on campus Tuesdays and Thursdays, and so we're learning new material on Tuesday, so that's not good.
Right.
I'm not getting able to see this move for 2 weeks.
I mean, you could do it the following Tuesday if that's not too
Following
big.
Tuesday.
Yeah.
So pretty much not this Tuesday, but the one
Right.
after.
Yeah. Exactly.
Okay. Yeah.
Yeah. If something else comes up, like maybe I could have another teacher administer it to you.
Okay.
If I could find somebody, then I'll let you know. But we'll go with that as the plan a week from Tuesday, unless I find something, and then we'll talk
Okay.
about whether
That's
that
perfect.
works.
So I would ask you again on next class Tuesday.
Yeah. Sounds good.
All right. Thank you.
All right. No problem. Bud.
I was late.
I got you.
I was bringing out supplies for an event. Sorry.
Oh, okay.
Liar.
You weren't there.
Yeah.
You guys want
You must have an event every class.
quick question about the computer project. When you say we're supposed to specify what each slider does
Yeah. So just
for all of them,
yeah.
for all the graphs, is it?
But some of those
might be the same.
Yeah. So what you could say is for each of the graphs below,
Slider
A does this, like
All right, and
that
I have
streamlines
there's like
things.
multiple graphs.
Yeah.
Like 7.
Yeah, you should have a lot of graphs.
All right, perfect, cool.
A lot of duplicating, and then changing things a little bit.
Yeah. Like, all right, cool. Thank you.
Professor, what did you tell him about the words? Would we
So,
have to
like
write?
for example, the A, B, and C values, they're going to change the same thing on every graph. They're going to impact the translations. So instead of writing that every single time, you could just write it for all the graphs below. A does this, B does that, C does that. It's only in each case you should stipulate what the unique variables associated with that graph.
So
take-
like what? Do that? Like what?
like for example, an ellipse has denominators where a sphere doesn't. So you'll have the A, B, and C values for both the sphere and the ellipse that'll do the same thing, but the denominators, the D, E, and F values for the ellipse are going to do something else. So you could say A, B, and C controls the location, but then for ellipse specifically, all you'd have to say is what the D, E, and F values do.
Just the words part.
Yeah. Attendance, okay. No problem.
Did you take attendance?
I did, yeah. You were here, I got you.
Oh, okay.
Yeah.
And professor, for the test, should we study the breakdown or study everything just in case?
The breakdown.
For sure.
Yeah. Once you see it, you'll know why.
Okay.
Yeah.
Thank you.
No problem.
I don't like it. It was interesting, but
I've never been there either. I've only seen it drop on a boat going by.
they're more like marine based, so like them have.
Just a little southpaw for you. All right, anyway, on page 16, we have this, it is a very relatively simple problem where it asks us to evaluate the iterated triple integral. All right, but this is really no more challenging than any other kind of triple integral because the units have already been converted over. Right, so instead of being x, y, z, it's rho, phi, and theta. So we're already at the point where the hard work has been completed. So now we just have to integrate. But the purpose behind this question is to just demonstrate that once you get to this point, you're really kind of in the home stretch. Maybe in the end game. Best movie of all time. So antiderivative 1/3 p cubed, because we're doing it with respect to p. I'm calling it p because I'm not going to say rho over and over again. So sine of phi on the interval of 0 to 1. All right, through direct substitution, it's just going to end up giving us a 1/3 sine of phi. All right, because the 0, it becomes irrelevant. All right, so the next stage of the game is integrating that over the interval of 0 to pi over 2. Why I had to stand up for that, I don't know. All right, so in that case, we're looking at negative 1/3 cosine phi over the interval of 0 to pi over 2. All right, so not terrible. Requires you to know a little bit of unit circle stuff, but not the hard unit circle stuff. So that's not bad. The first part zeroes out because cosine of pi over 2 is 0, but the second part gives you a cosine of 0, which is equal to 1. So we're looking at negative 1/3, which is a positive 1/3. All right, and so that's getting integrated over the interval of 0 to 2 pi. All right, so we're looking at 1/3 theta over the interval of 0 to 2 pi, which is going to give us 2 pi over 3. So we got a number. It's a good looking number, as numbers go.
Why did the P go away?
Why did it go away? I replaced the P with a 1.
Oh.
So it just cleaned up. All right. So this in and of itself is just a math problem that gave you a number for an answer. All right. But what we want to do is talk about what all of these values represent, what kind of meaning they have. And once you see it in context, it'll start to make more sense. All right. So that's where that little applet that I sent out the other day, a week ago maybe, comes into play. I'll pull it up. I sent it out on Remind. I'll pull it up right now and I'll show you. And then everything will be revealed. Now, because I'm freehanding it, it's not going to be pretty. We get x, y, z. We're going out to 1. But again, all the space in between 0 and 1. All right? So it's not just the surface itself, it's all the volume contained within the surface. All right? So then that's going to get us this guy. So all of that area. All right? So an attempt at a perspective drawing, so it doesn't look like that's a right angle, but it's supposed to be. All right, so we're talking right angle. And then it gets spun around. And that's where my diagram falls flat, because I can't really draw, as you know. So, you know, you might do something like this. Just to give like that little wedge of it, but you're spinning all the way around. For a total of 2 pi. So 2 pi in this direction, pi over 2 in this direction, with 1 unit above. Now, back in the day when I was sitting in Calc 3, we didn't have, you've heard this spiel before. This is all with chalk on chalkboard. And this was the diagram. And it was like, aha, yes, I understand clearly.
Back in my day.
Yeah, back in my day. In reality, it's like, all right, so what do you put where in the integral? Because I don't know what the hell that's supposed to be. But that, hopefully the applet helps, and you have access to it, so play around with it.
If we switch the values of phi and theta, would we result with the same answer?
No, because if you switch, if this goes from 0 to 2 pi, phi would spin around twice. So instead of going down and stopping at negative z, it would come back up, grab positive z, and then go back around, no, 2 pi. So it would only go around once.
But then it's going to be the same shape. It's still going to be a semi-sphere.
Right, but then it's only going to go a quarter of a turn from there.
It's going to be like the other side. It's going to be along the z-axis rather than...
It's still
Right.
going to have the same volume.
Not that I know of. Because it wouldn't create the same figure. Because you would only have, you'd have one full circle, but then you'd only turn it once. So it wouldn't give you the entire figure. Now, if you were actually to switch the variables themselves and integrate with respect to theta first and then phi, that's fine.
No, but then it's just the same equation.
Yeah, exactly.
I think actually, if you have, okay, so a 2 pi means it wrapped around the entire axis and came back in your diagram. This is a little bit clearer with how you do. Okay, so
That's why I use the applet.
yeah, so if you had a full sphere and you wrap it just a quarter, you have the volume of half a sphere, which is the same as if you just took half a sphere and rotated it
And it has the other side of it too.
around once. Like, the volume of half a sphere, be it half a sphere arranged in the top half, or in a swoop around the quarter turn, that's 2 quarter turns, that each have a volume of a quarter.
No, we're developing the shape. There's an order to developing the shape, and by using that order, you'll develop a different shape each and every single time.
I think it's a different, layout.
I think you're getting the full sphere.
Yeah.
No, because you didn't do a full sweep.
But as one side turns a quarter of a turn, creating one half of a sphere, the other side is also going to turn.
A quarter turn does not make
But you have the other
half
side.
of a shape.
I mean,
Like, a
geology
quarter turn
is
just
very-
makes half a
Let's
shape.
do it in,
Saying.
let's do it in geometry.
No, you do the second side.
It's-
Same thing we just
You're
used.
trying to get
You can't.
quarter on
Oh,
either
right.
side.
So once you
Yeah, but it won't. The parameters don't let me go out that far for
So,
phi.
Professor, we have the circle, and we're making it 3D basically. We turn a quarter, we get a half of the circle now.
Yeah.
Kind of like that.
Both sides turn. It's
Yeah.
like what you're
Area,
Yeah.
area
Yeah,
wise.
area-wise.
Right, and as much as I'd like to continue this conversation, it is the difference between you getting out of here at 7:15 and out of here at like
It's not going to be
8.
the same shape at all.
Next question.
So,
Back to the. It's going to be
All right,
material.
learn from that.
so
Back to the material.
yeah, it's a. So on the next page, we formally discuss the general rule, because what we get from this idea, the rho squared sine of phi and all the d's afterwards, is that this component, this part of it here, is the sphere itself. So what you're looking at, hence the spherical coordinates, just like dx, dy, dz gives you the volume of an arbitrary infinitesimal rectangular prism. This will give you the volume of an arbitrary infinitesimal sphere. All right. What the bounds do is propagate the length of the radius and the two dimensions associated with the angles, so phi and theta, that allows it to generate a sphere of any size. All right. And so how do we do that when we're dealing with things like cones and things of that nature? Well, just like you can fill in a volume with infinitesimal rectangles, cubes, you could do the same thing with infinitesimal spheres. If they're sufficiently small, they'll cover all the gaps. All right? Sufficiently small means infinitesimal, meaning the radius is approaching 0. All right? Just like the dimensions of the cube need to be approaching 0 in order for the cubes to actually collect all the volume underneath the surface, the same would have to be true for a sphere. All right? So this part of it, and I'm making an educated guess here, I'm willing to believe that you are comfortable with me saying that if we were to convert dx, dy, dz over into spherical coordinates, multiply them together and simplify, that this is what would come out of that, to spare you from the actual derivation, which takes about 40 minutes. All right. That being said, it's kind of like how we went into cylindrical coordinates. When we converted over by multiplying, it's the same general idea, just a lot more work. All right. So you'll take it on faith for that, but it allows us to apply another density model by including another function within.
Wouldn't you need spheres of different shapes to fill a solid? Because if they're the same shape, then you have these gaps where they're tangential, like from where they're tangential to where they are next tangential.
Yeah, but if they're infinitesimal,
There's
then
still the gaps. You need something smaller to fill in.
go even smaller.
Yeah, but no,
To the
you
quantum
need
realm.
those sizes, and then you need something smaller.
Then go even smaller. Because you can. You can always go smaller and smaller.
But it doesn't matter how small you get because where it's touching, like you still have that hole.
Then fill it in with more smaller.
Yeah, that are smaller than your other spheres.
Because again, remember, when it comes to integration, we're not talking about what the volume is. We're talking about what the volume is approaching. All right, so what the volume would be if you could ever get infinitely many spheres into that interval or into that region. All right, same thing with rectangles, cubes, whatever you can think of. We're going with sphericals, cylindricals, and rectangulars because those are the convenient figures. But these are the kind of things that, they don't really seem to work on the macro level, but on the micro level, they make perfect sense because, again, it's what the target volume would be if you could ever get infinitely many spheres in there, knowing, of course, that physically you could never, but theoretically you can. So the challenge now is the idea that we need to take something like this. Look at this baby here. Sight to behold. We want to convert that over to spherical coordinates. Now again, we don't learn this for the sake of learning it. Okay, so sometimes we do. But we're not learning this particular topic for the sake of learning it. We're learning it because putting it in spherical coordinates takes something that would be a nightmare in rectangular coordinates and makes it much more manageable. All right? Because if I were to work with this as is, and by the way, it's doable. You could do it. You have the skills. Calc 2 did that for you. You would have to integrate this with respect to z, then substitute this stuff in there, simplify, then integrate that with respect to x, substitute all this in there, and so on. Eventually you come up with a numerical answer, it'll be fine. All right? It'll just take you the rest of your life to do it. No, that's not true. It'll take you like double the length of time, triple the length of time it would in spherical coordinates. Yeah, like a day and a half, day and 3/4. So what do? Well, we're going to use our spherical coordinate relationships and do some substitutions. But there's one that I regret in my infinite wisdom of saying, oh, I'm going to put the formulas here so we can all point to them and look at them and say, this stuff makes a whole lot of sense. The one that I didn't have in here that I really should, so I'll take this as a typo every time that there's a box here, is I'll take college algebra or trig content. That's really getting people in this course. No, it's crazy. It's one of those things. I mean, you may look at it and say, but we've taken the third test. Like, a lot of us might even be done with the course. Like, you're not done unless you've demonstrated to me that you know this freaking unit circle. Seriously. Like, honestly, more than the count three stuff.
It's just
Because you know what? Every moment of dead air that I've had to deal with in this course, I mean, we've talked about algebra when the sub was here. It's like, our algebra was terrible. That's your words, not mine. Like, every bit of dead air, like when it's like, and the answer is, the crickets, it was always unit circle trig. It's or some like basic trig concept. And it's like, oh my God, one day.
Except to like look inside like your mind's eye and figure out where exactly in the unit circle it is.
Like, hey, here's this cut feet math. We're taking a lot of steps back from this trigonometry real quick and bring it all together.
If we could just do that, it'd be great. So,
I think we should just have a class just called unit circle.
Cotton would love that.
I have a problem with teaching.
I just
I give you F.
I just wonder how the scores would be.
Oh, yeah. We get an F.
Sorry,
Kinda weird.
I couldn't help myself.
0.
So rho sine phi is equal to the square root of x squared plus y squared. All right, so put it down everywhere you have a box. Put it down there. Because, you know, when you're taking a test, open note test, when you're thumbing through looking for formulas, you never know which one of these pages you're going to land on. You're looking for a formula, and make sure it's on each one of them. And besides, the more you write it down, the more likely it is to stick in your mind. And maybe it'll be there when you need it. All right. And I'll talk more specifically about the do's and don'ts for an open notes assessment in my class. Some rules I think are obvious, but some are not. So I just want to be as clear about things as I possibly can be. All right. Anyway, so enough about that. We have some obvious conversions.
our code on p squared.
Yeah, we can say p squared. It's fine. You know, I go back and forth on whether I call it one thing or the other. All right. So we know we have a rho squared in here. All right. So we're integrated because this is talking about the volume. So everything except for this bad boy right in here, the x squared plus y squared plus z squared, everything except for that is talking about the volume of the sphere. All right. This defines the sphere, and this information gives us the parameters for the sphere. All right. But in terms of x and y, so we're going to have to really consider what that means in terms of phi and theta. All right. That's going to be the big kicker here. But let's talk about these two bad boys for a sec. All right, so I'm just going to off on the side here rewrite z equals the square root of 18 minus x squared minus y squared. I'm going to square both sides, all right, because I have rules on the side there, and not many of them look like anything like that. So square both sides. If I add x squared and y squared to both sides, I get something really nice. All right, what I get is that rho squared is equal to 18. Which means rho is equal to, you could just write root 18. You could also write 3 root 2 if you want. Doesn't make a difference. All right. So that's the equation of a sphere. Now, it wasn't when we got to the rho equals root 18 that I realized it was a sphere. It was back here, x squared plus y squared plus z squared is equal to 18. That's like 2 months ago, when we were talking about spheres for the first time. Okay? That's the standard form for a sphere. all right, centered at 0, 0, 0. All right, so we're good there. Now, just thinking back to the applet, if I want to get out to root 18, it's not that I'm starting at that surface. I'm covering everything between 0 and that surface because I want the volume, I want the space contained within. So this is the outer boundary. We're going actually from rho equals 0 to rho equals root 18. All right? Because again, if we're talking, I'll just do a quick terrible sketch. Here's root 18, for example, on the z-axis. I'm starting at 0 and I'm trying to get all of that space in between 0 and root 18.
How do we know that we're starting at 0?
I was going to exact
Bottom,
the same
right?
The
thing.
bottom is not equal row square.
Wait for it.
Okay.
I was going to ask the exact same
Yeah,
thing.
you square both sides. You minus that piece.
So z is equal to, now the key ingredient here, I think probably more than anything else, is the idea that these two are bounds in the XYZ coordinate system, the rectangular coordinate system. But they're not necessarily the bounds for the same variable in the spherical system, all right? Because we can define quadric surfaces one way, we can define other types of surfaces in different ways, all right? So we need to let the math kind of take us for a ride here and see where we end up, all right? So I know, for example, that z, just going to my little cheat sheet over here, z, we could write it a few different ways, but this is the most convenient way, rho cosine of phi. But I also know that nifty new formula over there, rho sine of phi is equal to the square root of x squared plus y squared, all right? So rho cosine of phi is equal to rho times the sine of phi. All right. Now I can divide both sides by rho cosine phi. On the left-hand side, I get a 1. On the right-hand side, what do I get? Tangent of phi. All right, so phi would have to be equal to what? Unit circle. Pi over 4, good. Nice. All right, so that's telling me that, well, first off, it's telling me that I'm working with a different variable from the sphere, all right? The spherical coordinate system is kind of defined based on the equation of a sphere. All right, so rho dictates, and just like a circle is really defined by its radius, a sphere is defined by its radius. All right, so rho is the most important part of that equation, just like r is the most important part of a circle equation. All right, when you're getting to other types of surfaces in 3-space, rho doesn't always play a role in that. All right, really, if you think about it, a phi value of pi over 4, this surface, we've dealt with this before. This is a cone, all right? This is a hyperboloid of one sheet, which creates those two end-to-end cones, or tip-to-tip cones, all right? If you define this based off of its angle and spin that angle around the axis, you have the cone, all right? So the most important variable when it comes to a hyperboloid or a hyperbolic cone would be phi. All right, so what this is telling me, just kind of bringing it in a sec here, is I have pi over 4 is somewhere out here, and that we're sweeping through all of that area. All right, so it's a movement of pi over 4 off of the z-axis. All right, specifically, in this case, it's telling me that I'm starting at 0 and going to pi over 4. All right, so the previous one, it was the case that I was going, bless you, from rho equals 0 to rho equals root 18. Now I'm going from phi equals 0 to phi equals pi over 4. All right. So that took care of the z variables. It seems to have given us everything except for theta. Now I just got to figure out where theta lives. All right. So essentially, just thinking back to the applet, am I spinning this around the z-axis fully? Am I only spinning it around part of the way? All right. Or am I spinning it around more than once? In which case, I get an overestimate of the true volume, which would be dangerous. All right. So for that, I'm going to take a look at x equals the square root of 9 minus y squared. So square both sides. And you get x squared plus y squared is equal to 9. So this is a circle with radius equal to 3. All right, so now I'm going to draw the whole circle. But I'm going to bear in mind that I may not need the whole thing. Now, maybe I do need the whole thing. It's all going to come back to this information here. I'm going from 0, x equals 0, out to the boundary of that circle. All right, so you think to yourself, well, where's x equals 0? X equals 0 is here. The boundary of the circle is obvious. I'm going outward toward that boundary. But then for the y's, I'm starting at y equals 0. And I'm going to y equals 3. So I'm only capturing this little piece here. All right? So this is the case where you have to actually consider it, and I think the diagram makes the most sense when it comes to this sort of thing. All right? So what we want to do is, just thinking back to the angles that we would use in a unit circle, I would want to identify the starting angle for this region and the angle for which the region ends. All right, so where does it start? 0. Where does it end? Pi over 2. All right, so now we have all of our parameters. All right, it just took all this to do it. Now, this is a nice question, and you will have at least a couple. I can't, off the top, you know what? I'm not trying to be coy. I just honestly don't remember.
Oh, that's 3, right? In your hands?
Oh, yeah, it's a test. Yeah.
Is that the test?
Yeah.
He's looking at we're looking at the reflection from your left.
It's what's your left.
Oh my god, that's the test.
I think I copied up the wrong version of it. Dang it. All right, well, anyway, there was supposed to be 2 questions on here where it says, write an integral or set of integrals that could be used to find the volume of. Dang it. Well, that sucks. That's 30 copies. All right, well, I'm going to still go with that. I'm just going to tell you that question this and question that are the ones that you only need to set up the integral. Because I was editing 2 tests today, one for AP Calc and one for this, and I think I did it in that class, but not this class.
So you're going to give us the calc test then, right?
Oh, you don't want that test.
So theta's from,
AP Calc is brutal.
theta's from 0 to pi over 2.
Correct. Yeah, the way the questions are asked, they're not designed to be procedural. They're designed to be like, I don't even know what it's asking. Like, seriously. And it's not me doing it, it's the AP people.
You said that you were going to explain to us why we kind of like just let the boundaries go with it, you know, from 0 to that value, from 0 to that value. I felt as if we didn't start from 0, and you said you were going to explain why at some point.
I thought I did.
No, for rho and for phi. I'm looking at for
Yeah,
example,
because we have to
phi.
sweep through that interval. So it's not just the surface, it's the volume contained between the, like, if you have an entire sphere, if I were to just define it by just the root 18 and just the pi over 4, that would only give me the outer boundaries of it. It would give me no substance. It wouldn't give me anything within.
Which is why we have to check the lower bounds. But
Right.
You said automatically like 0.
But these two bounds are not related to one another. They're two completely different variables. So if I want substance, if I want it to contain all the volume, all the space within the boundaries, it has to start somewhere. Now, in this case, if you really consider it, if I start at rho equals 0 and go to the outer boundaries, I'm covering all the space that could exist within the surface. Then if I start with the angle of phi equals 0 and then work my way out to the outermost part of the boundary, I'm also covering all the space between the starting point and the outermost portion of the boundary. So I'm covering all that space, which is ultimately what I'm looking for.
Are we going to work with any problems where boundaries don't start at 0?
The only cases where that would happen, I would say, I think they'd be obvious in the problem just by the way the question is phrased. Like it would have to tell you,
We're
like
starting at negative pi over
or
2.
yeah, like bounded between the surface and z equals 1 or something like that, where you're not going all the way down to the origin. You know, so like it would be pretty obvious in the setup that you would know what you're up against.
So, like in this one, we're assuming that the radius is radical 18 positioned at 0 to radical 18. It can't be below, like it can't be a displaced sphere we're discussing.
It could be. We're not going to do that because, and this goes back to what we were talking about with cylindrical stuff. I don't feel the need to do it because my first step when it comes to dealing with anything that's displaced would be to translate it so that its center is at the origin and then do all the stuff anyway. You know, so like I don't feel the need because like if you have this skill down, then you can always modify this skill to handle anything else.
So if you didn't have if you didn't start at 0, let's say for row, let's say would that be like a cutout on the top, kind of like?
It would be more like
if you started a little bit after. Would it be like if you didn't go like the full rotation?
I would say it'd be more like a munchkin without the jelly inside. Like it would be a hollowed out sphere, but not completely hollowed out. There would be a spherical region on the inside that contained no volume.
Well, that's what
If you did that for row, if you truncated row.
The first example that looks like that is what you're referring to.
So if you're not starting from 0,
where the bound is not 0, that
yeah, you're starting from.
Right.
So that's what I thought we were going to go to at some point. That row does not.
Oh, you're talking about this
0.
diagram?
Yeah, this diagram.
Oh, this
That's a nice
diagram is
example.
just showing you what an arbitrary XYZ in a spherical system would look like. Yeah, it's unrelated to this example.
Okay,
Yeah.
but if our bounds were in 0, starting at 0,
start
that's
at
what
0,
you get.
started at
Yeah, then you'd have kind of like a washer method kind of thing from Calc 2.
Okay.
Yeah, along those lines, yeah.
Kind of shell in 3 dimensions.
Right. So then in terms of actually writing up our triple integral, we're done with the hard work. I mean, it's just a matter of writing it now. All right, so 1, 2, 3. Theta is going from 0 to 2 pi. I'm sorry, pi over 2, because that's what we just figured out, but it was a while ago from my perspective. Phi is going from 0 to pi over 4. And rho is going from 0 to root 18. We have rho squared times rho squared sine of phi, part of the rule. Oops, undo. d rho, d phi, d theta. Now, we're not going to actually integrate this because the question's not asking us to, but you compare this to the one that we did on the previous page, it's maybe slightly more difficult, but not in a meaningful way, because first thing you would do is put the rho squareds together and make it rho to the 4th, and then when you integrate that, it's 1/5 rho to the 5th, and then you're subbing in more complicated values, but nothing too crazy. All right, so very, very doable. All right, maybe like 2 minutes worth of work if you're going slow. All right, whereas we talked about this long time. All right. Day and a half, like half a heartbeat. Nothing too crazy. All right. So the obvious benefit of converting to spherical coordinates, I think, is right in front of you. But the unfortunate thing is you got to do all this stuff to get you to the point where you can write the integral. Right? Now, with experience, this part of it goes a lot quicker, but it's still preferable to do it this way rather than to live with the integration that might emerge in the substitutions and nastiness of algebra that comes from this. Because, I mean, aside from not being an elegant approach, it just takes a while. And so efficiency becomes the name of the game. All right?
Where do we get the p squared sign? P squared sign?
Oh, that's part of the rule.
Oh.
You want to put a E there.
Oh, okay. Oh, yeah, we're missing that.
You're missing the angle. B.
I didn't write it in? Oh.
Can you take the angle of D feet?
Can
Is
I?
that the question? I guess you can put each bullet into a function.
That comes from this diagram here, where we said that we're dealing with a circle because of this equation, x equals the square root of 9 minus y squared. But then it's going from x equals 0 out to the circumference, but then y equals 0 out to y equals 3. So it's trapping only this interval, which starts at 0 and ends at pi over 2 if you're spinning around the circle. All right. So number 2, I think maybe I'll just put an answer key up for this one because it's really just, it's the same as the previous page. It's just, it has a function of x, y, z plugged in. So it's kind of maybe slightly a more challenging version of maybe like a hybrid of the last problem on the previous page and this one, but it doesn't really advance the plot, or at least as much as the next one does. So let's next one. We'll do that. And then we'll go from there. Oh, and number 4 is not happening because I have to teach an entire, like, yeah, it's involving determinants, matrices with partial derivatives. So
I can cross the number 4 out?
yeah, you could toss it because you're not going to be on the hook for it.
I'm gonna throw my Lynch algebra background without.
Yeah, it's a pretty cool concept, but it's like a good week to understand it.
Oh, okay.
Like, I mean, because actually doing it is very, very easy. Understanding why it works is the thing that takes a little while. So,
Yeah.
and I don't want to go down that road. Explain something and just like, oh, here's another thing you have to just take on faith. Right, so I'm just gonna, again, like I said before. That's a pretty useful one. All right. So what we're looking at here is another case where you're dealing with a cone inside a sphere, but it's just going to have different parameters. So you're getting another taste of a similar concept, but this time we're going to take it the distance. All right. So solve for z in both cases. It's not given in rectangular form in terms of an integral, so we have to come up with the spherical triple integral. We don't have to stop off by finding a rectangular triple integral. We could just kind of cut to the chase question.
So this is what's outside, like it's the volume of the sphere minus the volume of the cone, right?
If you're doing it in rectangular form, yeah.
Okay.
All right, so what I want to do first is define my functions in spherical coordinates. I've only been to the southern hemisphere once in my life. Sorry, I wrote that too big, so I'm just cleaning it up. South Africa. South Africa.
Is that where you're gonna go your next vacation?
No, that's where I went for my honeymoon 10 years ago. Apparently, I have to go on another lengthy plane flight for the 10th anniversary. 'Cause she wants to go, where the hell is it? Indonesia.
What is that?
Did you say Thailand?
Yeah, but that's a stopover on it. So it's Thailand, but then what's the name of the city in Indonesia? I mean, there's a few of them, but I'm trying to think of the one that we're going to. Bali? Is that in Indonesia? Bali? Yeah. Yeah. Okay, so that's where we're going. Yeah. Yeah, for a person who has white knuckle terror on a plane, that's going to be interesting.
Did you get that from the student info sheet?
You know what? I'm not going to lie. It did come up in conversation, and it might have, because I don't really have any control over this stuff. But I did tell her I had this cool idea of putting this question on the info sheet, and she did ask what some of the responses were, and I saw the wheels turning. I would not be. I got to ask her when I get home. Like, did you do that because of that?
Next person won't be
Will
there.
she create the info sheet or?
No, but like I put that on there just like as a getting to know you thing.
Oh.
But then ultimately it turns out that I think we're ending up like stealing people's dream vacations, and it's really just like not nice. But
During summer, like,
like, sorry, sucker, you didn't get to go, but I did, and it was great. Send out pictures on Remind. That's beautiful here. So anyway, I factored out the radical 3. I mean, I didn't really factor it out. It was already factored out. I just separated it. The z is rho cosine phi. Poor quality phi. I mean, they're all poor quality, but that took the cake. Root 3 times rho sine of phi. All right, so I can clean it up. So what I'm going to do is pretty much the same thing that I did in the last question. I'm going to solve for tangent, which means I want to get sine over cosine as the only thing on one side of the equation. So I'm going to divide both sides by rho cosine, because I know the rho's are going to cancel. But I'm also going to divide by the root 3. So that the root 3 and the rho cancel, leaving me with just a tangent of phi. And on the left-hand side, it's just 1 over root 3. That is nowhere near what the symbol was supposed to be. So I just have to think back to my astounding knowledge of the unit circle and just pull that information from the depths of my brain. What is the angle that has a tangent equal to 1 over root 3? I'll give you the pi over part.
6.
Pi over 6. Yeah. So that rationalizes to radical 3 over 3, if that makes it any better, but it's 1 over root 3, then 1, and then root 3. All right, as you work your way around from the x-axis.
Isn't there a second spot where tangent equals 5 by square root of 3?
Yeah, so that would be at 5 pi over 6.
You're not bothered using that?
No, because we can get what we need from pi over 6 and spinning around.
We're going to spin anyway.
Right. So, and also, in this case, since we want to live above the x-axis, you know, if we're thinking in 2 space, that's
part. Yep.
or the xy plane anyway. All right, so then the other part. So we have that. So we have a way of defining in spherical coordinates the cone part of it. Now I just need the sphere. So 4 minus x squared minus y squared. So
ace these fucking quizzes.
Z squared is equal to 4 minus x squared minus y squared. So x squared plus y squared plus z squared is equal to 4.
It actually tells us something.
It tells you what
Yeah,
the
it tells
radius
you
is, because it tells you
Not
where
top of
it
the
is.
chart.
Oh yeah, you could just count it. Yeah, I guess. Sounds good.
That's cheating.
Yeah. Gotta learn the skill, cause I think I copied this from OpenStax. I made my own graphs for the test. They don't have labels on them. They barely have graph on them.
You
So.
draw them by hand?
No, I GeoGebra'd it, but they're. I mean that they look pretty decent. But the only thing I really needed to get across to you when it came to the graphs was just like what kind of surface you were up against. You know, like aside from that, everything else is really analytic. All right, so I have boundaries for phi and I have it for rho. We're looking at the entire semicircle, the entire cone, and then the relationship within. So we're pretty good shape there. So now what I need is some way of figuring out theta. All right. So that theta is going to be related to whatever the boundary is that relates to this part, which would be the intersection of the cone and the hemisphere. I almost said semicircle. What's that?
You can't just say 0 to 2 pi then.
Well, that's what I'm getting at, all right? But we're gonna do it analytically anyway, just because we could be dealing with situations where it's not 0 to 2 pi, so we want to get the skill down.
So it's just the baby, the sphere on top? It's not the volume of the hemisphere minus the volume of the cone, it's just
Well, it's the ice cream cone.
So then are we calculating the
not-
top
so
part
I-
as well?
I've been sitting here as to what we were going to turn, the one that has, looks like a Y into.
Is the ice cream part of the volume?
The ice cream is part of the volume.
Okay.
Is it a waffle cone?
It is. I mean, because why wouldn't it be?
Exactly.
Yeah, like, we're not going to be ridiculous around here. Keep some semblance of normalcy.
And that's where the pi over 6 starts, right? Where the cone actually.
Yeah, so this part of it is your pi over 6, right? So it's sweeping through the pi over 6. We're gonna come up with the equation of this analytically. Again, just because there are circumstances out there where even though you look at this, you're like, it's clearly 360 or 2 pi. It won't always be, so we want to make sure we're doing that the right way. And then also the other component is the rho value. All right, knowing that rho is going from 0 to 2, really, if you consider it, it's all the space that exists between the origin and the surface of the sphere. All right, following along pi over 6, or at least as far out as pi over 6 as you work your way out from 0. And then once you spin that around the z, then you have the entire requested or required interval.
If you started at pi over 6 and like went around it, that's the phi, right? That's
Right.
okay. Okay, that's what I was looking at before.
So to get that intersection, it's just a matter of setting our two equations equal and solving. Square both sides, get rid of those radicals, and I'll distribute while I'm at it. The other reason why I don't have a problem taking the time to do this work here is because it's not hard. I mean, I'm just going to add a couple of terms to both sides. I'm going to get 4x squared plus 4y squared equals 4. Simplify, and you're going to get the unit circle. Man, that keeps coming up over and over again. So you're looking for any kind of restriction that might exist, and it turns out that we don't have any. But in the xy plane, this is going from 0 to 2 pi without, like I said, without any restrictions. So we now have confirmed analytically that our bounds for theta will be 0 and 2 pi. All right, so we have what we need there. So we're looking at an integral from 0 to 2 pi, 0 to pi over 6, I think is what it was. 0 to 2. All right. All of that defines the figure that we're looking to find the volume of. So the only thing that's left, we don't need a function of rho, theta, and phi. It's really just rho squared. I should do that in the same color. It's confusing the other way. Rho squared sine phi d rho d phi d theta. All right, because ultimately, I mean, and this is the beauty of spherical coordinates, if you have a figure that's encased within a sphere, you're really just looking for the part of the volume of the sphere that is the thing that's encased within it, right? Because this whole thing is a hemisphere. Part of that hemisphere is the cone. So basically, I'm just trying to trim off the parts of the sphere, the hemisphere that I don't want. These bounds do that, all right? I knew I had to go out to 2. So that, I mean, if I left this at 0 to pi and 0 to 2 pi, that would have given me the whole sphere. But by trimming this to pi over 6, that cut off all of this stuff. And by spinning it around the whole way, that gave me the cone that I was looking for, but with the extra bulb on the top that we needed to basically simulate the ice cream cone shape that we wanted.
So if you just put rho squared, that'd be the whole sphere.
If we did 0 to pi, that would have been the whole sphere.
No, I'm saying for the function, like rho squared times rho squared times phi.
No, because these bounds, the triple integral itself gives us the volume of a sphere in general, right? This information dictates what part of the sphere we want.
Okay. So the top part, that ice cream part that I was referring to, that's not actually part of the volume.
It is.
It is. No, the top head.
Yeah. That's in there.
But it's an angle and then it's spun around. How are you getting the top part?
Because we're going all the way out to 2. So I can go out to 2 here, that gets me there. But then if I go out to 2 in that interval, that's going to get me all the way up to the top of the bulb.
How are you cutting out the inside?
I'm not cutting out the inside. 0 to pi over 6 is what we're keeping. All right, so this isn't like...
so the top part you're not
It's
keeping.
not like you're taking out and just doing the outside.
Right. 0 to pi over 6 is saying I want, this is going to be included in my interval. I'm keeping this and
you're keeping the cone. You're not keeping.
Right. Everything else is gone.
I thought you were keeping the outside, not the inside.
To whatever.
No, yeah. If I wanted that, it would be pi over 6 to 2 pi.
Right.
Exactly.
Ah.
Right. So that's a good point, because if a question said, "Give me everything except for the part that's encased by the cone," then I would have to rethink of it. Yeah.
Oh, wait, I'm sorry. If you wanted the outside, what would it be?
It would be pi over 6 to pi over 2. Because that would get me from here down to the y-axis.
So you have an extra blue packet?
Maybe. Oh yeah.
That was a good.
Do you have an extra one from the other one? You got first one?
First. Maybe.
Like the first with the sub.
Oh.
Is it partial integration?
Yeah.
Double integrals of polar coordinates. I got 7 through
I have that one.
11. Yeah, I don't have the one before
Alright,
that.
I'll print it out from your website.
Okay. All right.
But I thought that on the website that you showed us, when it started at 0, it started off on the
Because you're going
X.
from 0 from the Z.
0 from the z-axis. Because we're always starting here. Now, if you're dealing with cylindrical coordinates, then you're going base up. So that might be the issue, if you're getting the two. All right, so now go in the distance here, and again, like in terms of finding the equation of a sphere in rectangular or cylindrical coordinates, it's not terrible, it's just not fun. This is really nothing in terms of the work that you have to do, because I'm integrating first with respect to rho. So 1/3 rho cubed times the sine of phi. Now, of course, I'm going to screw it up because I said this is really nothing in terms of its difficulty, so it's like guaranteed, but in theory it should be nothing. All right, so integrate just the rho squared because we're working with rho first. So that's just 8/3 times the sine of phi. Then I'm going to integrate, we'll do it a piece at a time here, from 0 to pi over 6, the 8/3 sine of phi d phi. So it's going to be negative 8/3 cosine phi, I think, on 0 to pi over 6. All right, so I pop in the pi over 6. So negative 8/3 cosine of pi over 6 is what? Square root of 3 over 2. Minus the negative, which is going to become a plus 8/3 because cosine of 0 is equal to 1. All right, so we're looking at, if I clean it up a smidge, 2 goes into 8 4 times. We're looking at 8 minus 4 root 3 over 3. That in turn gets integrated with respect to theta. Now, because this is constant, that's really just going to, I mean, we're just going to take this and multiply it by theta, which really amounts to just multiplying by the upper bound, because the 0 is just going to 0 out. So we're talking 2 pi multiplied by all that stuff, and that would give us the volume of the ice cream cone. All right, so 2 pi times 8, well, nah, I was going to factor out a 4 just to make it look a little nicer, but I've lost interest. 8 minus 4 root 3 over 3. Okay, I'm re-interested. So I couldn't leave it that way and then expect you to do it the same way in the test. So pull out the 4, so 8 pi 2 minus root 3 over 3, and that, ladies and gentlemen, is the course.